In this course, our interest in the derivative is rather more than just being able to differentiate. And to begin with, the definition is crucial to our work. So let's see how some intuitive ideas can lead to a rigorous definition of the derivative. Well, here we've drawn a tangent to the graph of this function through this point associated with the point C in its domain. And we think of the slope of this tangent as the derivative of f at C. Now this is probably the notation that you're used to for the derivative. There are of course others, and here's one of them. Read it quite simply as the derivative of f at the point C. And this is the notation we're going to use in our course. And of course, if you can find the derivative for all the points in the domain, then you've set up a function, the derived function df. Simply associates each point x with the derivative of f at x. Well, so much for the notation that we're going to use in the course. Let's get back to the definition. See, it must tell us the slope of this tangent. Now we can think of this tangent as a special type of chord. Here's a chord through the point. We can think of the tangent as the chord that we get when these 2 points coincide. Now we can work out the slope for this chord quite easily. In fact, the only place that we can't work it out explicitly is when these 2 points coincide. So it seems that there's an infinite number of positions that our special chord can take. Well, you might say that's nonsense, because if you look at the slopes of these chords, as this point moves towards the fixed point, the slopes vary continuously, and as we go through the point, they carry on varying continuously. So this continuous variation should just give us one position for our special chord. The only problem would be, of course, is if these chords gave a sudden jump as we went through the point C. But continuous variation should give us what we want. So we must now say precisely what we mean by continuous variation. Well, we're going to get it through a function. It's a function that will give us the slope of such a chord and which will be continuous at the point C. Peter?
Well, let's look in a little bit more detail at Tim's chord slope function. Here's our fixed pivot point. Here's another point on the graph corresponding to x. Here's the chord through the 2 points, and its slope is given by this height divided by this length. Well, as we vary x, we vary the corresponding point on the graph and the corresponding chord and its slope. So we get a function, and for each x, it gives the slope of the corresponding chord. So, naturally enough, we call this the chord slope function. And we write it like this, capital F subscript C. The subscript C tells us where the fixed pivot point is. For instance, if we pivoted at the point corresponding to 0, we'd write capital F subscript 0. Well, Tim's already told us that in order to get a unique slope for the tangent, we're going to want the chord slope function to be continuous at C. That's just this condition, and then the value of the chord slope function at C just gives us the slope of the tangent. That's the value of the derivative at C. Well, that's what the chord slope function is. Let's try and find a formula for it. For our particular value x, we want the slope of this chord. That's this height divided by this length. That's f of x minus f of c divided by this length, which is x minus c. So we obtain this formula. The only problem with this formula is when x equals c, in fact the point we're most interested in. You see, this side isn't defined when x equals c because we can't divide by 0. So we have to have this restriction. Well, how do we get round that? What we'll do is we'll look and show you how we get round it for a particular example. The particular example we're going to look at is the function f of x equals x squared. Then this difference here just becomes x squared minus c squared. And we know how to divide this. We get x plus c. Only we still have a problem. This equation still only holds when x is not equal to c. So we still can't get a value of the chord-slope function when x equals c. But there's one condition we haven't used yet. We haven't used the continuity condition. And that's going to be exactly what we need. Well, let's see how that works. What we do is we look at the graph of the values of the chord-slope function that we already know. It's just the graph of x plus c, except with a gap here, because we don't yet know the value at c. But we do know that the function has to be continuous at c, so it's pretty obvious what its value must be. Must be just here. So what we've done is we've used the continuity condition to fill out the graph of the function x plus c. So continuity tells us that this formula holds for all x. So the value of the chord-slope function at c is just c plus c, that's 2c. So the value of the derivative at c is just 2c. Well, we can do that for any number c. So we find that the derived function for the function x squared is just the function 2x. Well, in this case, we were able to use the continuity of x plus c, and everything was straightforward. But to stress the importance of continuity, let's look at a function that isn't differentiable, a function for which we can't find a chord-slope function, because we can't satisfy the continuity condition for a chord-slope function to exist.
Consider a function that has a graph shaped like this. It has a cusp at this point that corresponds to the point C. Now, if you look at the chords on this side of C, you'll see that as the free end approaches C, the chords get steeper and steeper, until at a point quite close to C, this chord's quite steep. Now, for the points past C, as the free end moves away from C, you'll see again the slope increases, but at a point near to C, the slope's quite small. Well, we can see this behavior more accurately on this graph of the chord-slope function, where we plotted the values of the chord-slope function for all the points, except, of course, for the point C. Again, you can see that as we approach C from this side, the slopes increase, and at a point just after C, it's suddenly quite small again. Now, there's no one point at C that I can choose that makes this the graph of a continuous function. So in this case, there can't be a chord-slope function, because you'll remember an important condition was that the chord-slope function is continuous at the point C. Now, what this means on the graph for the function f is that there's no one position for a unique tangent at this point that avoids a jump as we move from these chords through to these chords.
Well, now you see why continuity is important in our definition of differentiability. In order to ensure that our function is differentiable at C, we need to find a chord-slope function satisfying this equation when x is not equal to C, and satisfying this condition that it's continuous at C. Well, let's tidy this equation up a bit. You see, it's rather awkward to use in proofs because of this quotient and this restriction. So what we'll do is we'll cross-multiply by x minus c to obtain this equation. That's just this difference is equal to the value of the chord-slope function times this difference, and there's nothing strange about that. That corresponds to this geometrical fact that this height is equal to the value of the chord-slope function, that's the tangent of this angle, times this distance. But the nice thing about this equation is that it holds for all x. You see, when x is equal to c, this side is 0, and this side is 0. So, in fact, we can use this as our formula for the chord-slope function, as long as we remember to use the continuity condition at c. So, let's write out both of the conditions together. This is the definition we'll use of the chord-slope function. And the function f is differentiable if such a chord-slope function exists. In which case, the derivative at c is just the value of the chord-slope function at c.
So we finally have our full definition for differentiability. And let's use it immediately to prove an important result that says if a function is differentiable at a point, then it's continuous at that point. You see, if it's differentiable, one whole, so the function f is this constant added to this function times that function. Now this function is continuous at c. By the definition, this function is continuous at c. So the product is continuous there. And finally, f is continuous at c. So you see, the definition gives us a very simple proof for this general result. Now let's see how to use the definition to prove a result about a specific differentiable function.
In fact, I'm going to look at a whole family of differentiable functions, the exponential functions. Remember first what they look like for different values of a. As a gets bigger, the curves get steeper. So they all cross the y-axis at height 1, but the tangents there get progressively steeper. The value of a, for which the tangent is exactly at 45 degrees, is the famous number e, which is approximately 2.7. And something else you may remember is that the derived function is just the original function times a constant. You may recall from the foundation course that the value of this constant k is just given by the value of the derivative at 0, and that when a is equal to e, the constant is just 1 because the tangent is at 45 degrees, and so the derived function for e to the x is just itself. Well, we're going to prove this general result, relating the value of the derivative at x to the value of the derivative at 0, and as usual, we're going to prove it for one point at a time, and the particular point we're going to prove it for is c. So this is the formula we'll want, that the value of the derivative at c is equal to a to the c times the value of the derivative at 0. So what we want to do is to relate what goes on here at 0 to what goes on here at c, and we do that in terms of two transformations. First of all, we translate by a distance c to the right, and then we stretch this height 1 by a factor a to the c to get back to the curve. Well, the remarkable thing about these two transformations is that when we apply them to the whole graph, we end up superimposing it on itself. Let's see why that happens. Remember that translation to the right by c just replaces x by x minus c. That's true for any function. If we now scale this new curve upwards by a factor a to the c, we'll just be multiplying the function values by a to the c. And to multiply exponentials, we simply add their indices together, which gives us back our original function. So the translation, followed by the scaling, gives us back our original curve. And it's this fact which we'll use to relate the derivative at c to the derivative at 0. The way we'll do that is to consider the chord-slope function at c and relate it to the chord-slope function at 0. What I'm going to do is I'm going to use the two transformations to relate these construction lines for the chord-slope function at 0 to these construction lines for the chord-slope function at c. Well, you might realize that translations and stretchings both preserve horizontal distances. So we're going to want this distance to be equal to this distance. That is, I'm going to need the condition x dashed is equal to x minus c. Well, once I've made that choice, these 2 points translate across to 2 points here. Then when I stretch, this takes us back to the graph. That's how we define the stretching. And this one must stretch to a point at the same height. Then if I look at this point, well, it translates across to here, and when I stretch, I again get back to the graph. That's because we've shown the two transformations superimpose the graph on itself. Right, so what I've shown is that the corners of this triangle go over the corners of this triangle, and since translations and stretching both preserve straight lines, this triangle is superimposed on this triangle. Well, in fact, that's going to be just what we want. It's going to enable us to prove this result. And that just tells us that the value of the derivative at c is equal to a to the c times the value of the derivative at 0. Well, how are we going to get that? We're going to get that by relating this length to this length. You see, when we translate and stretch, this length is multiplied by a factor a to the c to give us this expression for this length here. Well, you may recall we had to choose x dashed equal to x minus c. So we obtained this alternative formula for the length here. Now, you should recognize this expression already. You see, what it is, it's the value of the chord slope function times this difference. And we just know that that's the first part of the definition of the chord slope function. And hence, it's just equal to the difference of the values. So it's equal to a to the x minus a to the c. Well, what have we got here? We've got something times x minus c. So it looks like this is an alternative representation for the chord slope function. And since the chord slope function is unique, it looks like these two expressions must be equal. That is, we have this identity. Well, that's exactly what we want. You see, if we substitute x equals c, we get this. And if we substitute x equals c here, we just get 0. That's what we wanted. Well, there should be one or two points that worried you in that argument. What I've said is that because this appears to represent the chord slope function, because it satisfies the first condition, and since the chord slope function is unique, it's an alternative representation of it. Well, you might first of all ask, represent what function? Well, the easiest way to think of this representing a function is to think of it representing a composite function like this. First of all, we map x by x minus c, and then we substitute for x dashed and map like that. That is, we use a to the c times this chord slope function. So this expression really does represent a function. But so far, we've only shown that it satisfies the first condition to be a chord slope function. In order to ensure that it is the unique chord slope function, we've got to show that it satisfies the second condition. That is, we've got to show that it's continuous at c. Well, let's have a look at the behavior of this at c. First of all, c is mapped by this continuous function to 0. And then 0 is mapped by this function, which we know is continuous at 0 because this chord slope function is. So this composite function is continuous at c. So this expression here really does give us a function that satisfies both of the conditions for the chord slope function. So it really is an alternative representation for the unique chord slope function. These two expressions are equal, as we said, and the result follows.
So we've now looked at two specific examples, x squared and a to the x, and we've used our definition to find their derived functions. Now, for the last part of the program, we're going to use the definition to prove a result about differentiable functions in general. This states that wherever a function has a local maximum or minimum, its derivative will be 0, provided the function is differentiable there, of course. Well, you probably often use this result, but of course now we're interested in its proof. Well, when you're looking at the proof of a general result, it often helps to look at a specific example, such as this one, the function x squared times e to the x. You see, this function has a suitably complicated graph, and also we know how to differentiate it. Now, you can probably do that yourselves, but if you can't, you'll find the details in the unit. And the derived function turns out to be this. As you can see, the derivative will vanish when x is equal to 0, and also when x is equal to minus 2. And this ties up very nicely with our graph. At x equal to minus 2, a 0 derivative at this local maximum, and at x equals 0, a 0 derivative at this minimum. But how do we go about to prove in general that at a local maximum the derivative is 0, and at a local minimum the derivative is 0? Well, first we'll need a definition of local maximum. When we say there's a local maximum at x equals c, what we mean is that there's an interval surrounding C where the function takes only lower values. Now the derivative at C is the value of the chord slope function at C, so this is what we want to prove is 0. Well, consider the values of the chord slope function at points near C in our interval. For chords through points to the left of C, the chord slope values are all positive. And for chords through points to the right of C, the chord slope values are all negative. And we can use the continuity of the chord slope function to show that its value at C is equal to 0. Well, consider the closed interval about C. In particular, look at its image under the chord slope function. You'll see that this image contains some positive values and also it contains some negative values. So that when we take the least closed interval containing this image, this least closed interval will have 0 in it. Now this is true for all closed intervals about C. So in particular, if we take a nest of closed intervals that converges to the point C, then the corresponding least closed images will all contain the point 0. But we also know that they all contain the image of C. Now, are these two the same? Well, the continuity of the chord slope function tells us that these least closed images form a nest that converge to a unique point. So these 2 points, the image of C and 0, are the same. And that's what we wanted to prove. We have the derivative of f at C is 0. And this argument holds equally well for a local minimum. So we now have our local extremum theorem that says the derivative at a local maximum or minimum, if it exists, will be 0.
So we've looked in detail at several things in this program, so I'll summarize them. First of all, we used the chord slope function to obtain a definition of differentiability. And then we used this definition to look at the derivatives for 2 functions. The first, x squared, was very straightforward. And for the second, the exponential function a to the x, we used a geometrical argument to show that its derived function was just the function itself times the value of the derivative at 0. Finally, we looked at a more general result, the local extremum theorem. That tells us if a function has a local maximum or a local minimum and it's differentiable, then the derivative at these points is just 0. And again, the proof used the continuity of the chord slope function. Well, in the correspondence text, you'll see several more results. One of them is the mean value theorem. But most important of all, I hope that today we've brought home the crucial role played by continuity in the definition of differentiability.